This is section 4.4 on Newton's second law. Our goals here are to understand the connections between force, mass, and acceleration as described in Newton's second law, and also be able to apply Newton's laws to some sample problems, and those problems involving some multiple directions. Here we're looking at a particle that is in fact under a net force. If you recall, Newton's first law explained what happened when an object had no net force acting on it. Basically, we said that it would remain at rest, or it could move in a straight line at a constant speed. In this case, from understanding Newton's first law, we can realize that forces must be those things that actually change the motion of an object. We would not say that they're the cause of motion, since we said that in the absence of a net force, something could continue moving at a constant velocity, basically same speed in a straight line. But forces have to be those things that are actually able to change the motion of an object. So Newton's second law basically answers that question of what does happen when an object is under a non-zero net force. And essentially what we see is that acceleration is going to occur. It's not going to continue at a constant velocity anymore, but that velocity is going to change when that force is there. So you have an acceleration, and that acceleration is going to be directly proportional to the net force that's being applied. Newton's second law would then state that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. We can see that in the equation that we have written down here. Newton's second law was first discovered and originated in this sort of a form, understanding how that acceleration is going to be affected when you have a net force acting on the object. Here, the sigma F is going to be our symbol for the sum of the forces acting on the object, or net force, and it is going to be a vector sum of all of the external forces acting on the object. If you take a look at this equation and instead write it as A equals net force over mass, we could also rearrange this and write it as F equals ma. This equation is one of those cornerstone principles in physics that can be used to solve many, many different types of problems. What we need to understand about F equals ma is that it is a sum of all of the external forces. Any internal forces would not be included as we're trying to sum up the forces acting on the object. And the reason for that is that internal forces do not have the ability to actually affect the motion of the object. You could think of it as kind of pushing on your own dashboard or blowing into your own sail. Internal forces do not have the ability to affect that motion. Only external forces are going to change the motion of the object and result in some sort of acceleration. Also, we need to understand that this F equals ma is also a vector expression, which means that we can break this down into various directions. We need to focus on one direction at a time. So we could sum up all the forces in the x direction and set that equal to ma to solve for accelerations in the x direction. We could also sum up all the forces in the y direction and set that equal to an ma to find the accelerations in the y direction, or even do so in the z direction. These would also be related to I hat, j hat, and k hat. So again, you want to sum up all the forces acting in individual directions and add those forces up and set them equal to an ma. What we want to watch for is that in these cases where we're utilizing F equals ma, is that as long as the force is constant, your acceleration will also be a constant. That's not necessarily going to be the case for all problems, so make sure that you watch for that and be sure that as you're working on a problem, if you are applying these equations, that you are accounting for constant accelerations matching with constant forces. If the acceleration is constant, does that then mean that the velocity is going to be constant? Think about that for a second. The answer is absolutely not. If you have a constant acceleration, by the very definition of what acceleration will change your velocity over the course of time. So with a constant acceleration, your velocity should also be constantly changing in either a positive or a negative direction, depending on the sign of that acceleration. The units for force is the Newton, and the Newton is actually a combination of kilograms multiplied by meters per second squared. Again, it's just following the equation that F is equal to ma, and we're plugging in those SI units there. 1 Newton is basically the force required to give a 1 kilogram object an acceleration of 1 meter per second squared. Let's look at an example of a problem where we would be using Newton's second law to solve for an acceleration. Let's say that we have a hockey puck, and it's going to be sliding along a horizontal frictionless surface, but it's going to be struck simultaneously by 2 hockey sticks, each one applying a different force in a different direction. Let's place our hockey puck on an axis so that we can use our forces and apply them according to the directions that are given. So I'm just going to sort of stick my hockey puck on the origin of an axis system here, and I'm going to draw out the 2 forces that are described in the problem. One of the forces is 5 newtons at an angle of 20 degrees below the x-axis. So this would be my 5 Newton force, and this would be a 20-degree angle. The other force described is an 8 Newton force, and it's applied at 60 degrees above the x-axis. So this would be my 8 Newton force, and this would be my 60-degree angle. Ultimately, the question is to determine the acceleration of the puck. Now, if we remember that we are using F equals ma, and that is also a vector problem or vector equation, we need to look at this problem by looking at various components to these forces, because we can only apply F equals ma in a single direction at a time. If I sum up the forces in the x direction, that will give me the acceleration in the x direction. And if I sum up the forces in the y direction, that could solve for the acceleration in the y direction. So let's start with the x direction first. I can see that both my 5 and my 8 Newton force would have a component in the x direction. Some of this force here is going to be in the x direction, and some of the 8 newtons is also going to be in the x direction. If I look at finding those components, I can see that some simple trig will get me those values. Starting with the 5 Newton force. The 5 Newton force, if I multiply that 5 by the cosine of the 20-degree angle, I will find this x direction piece, or how much of that force is in the x direction. The 8 Newton force also has a component in the x direction, which I could find by taking 8 multiplied by the cosine of the 60-degree angle. When I sum up each of these forces, I find that my total, and if you want to pause the video here, go ahead, pause it, pull out your calculator, and see what you get when you solve for this. When you add up all of your x forces, you get about 8.7 newtons worth of force in the x direction. Now when I solve for the acceleration in the x direction, I can set the sum of my forces, or 8.7 newtons, equal to the mass times the acceleration in the x direction. The mass of the hockey puck was 0.3 kilograms, and now I can solve for a sub x. In the x direction, again, take a second, plug this into your calculators. You'd find that you have an acceleration of about 29 meters per second squared. Now I have my x component to the acceleration. I'm going to write it over here and make some more room for the y direction piece. In the y direction, we're going to do something very similar. In this case, we're going to now look at components of each of those vectors that would be pointing along our y-axis. If we look at the 5 Newton force, we can see that it does have a component in the y direction. It would in fact be a downward component. And the 8 Newton force also has a component in the y direction. It would be upward. So each of these are going to have opposite signs. As I begin with the 5 Newton force, I realize that this is in the downward or negative direction. So as I solve for that component, I would use 5 multiplied by the sine of my 20-degree angle and stick a negative sign on that to represent that it's working against the 8 Newton force, or in the opposite direction in terms of y. The 8 Newton force also has a component in the y direction. It's going to be positive since it's pointing upward, and I could find that component by taking 8 multiplied by the sine of the 60-degree angle. Again, pause the video for a second, plug this into your calculators, and when you add these two forces up, you'd find that your total sum of all the forces in the y direction comes out to be about 5.2 newtons worth of force. Again, I can come back to my F equals ma equation, this time for the y direction, plug in the total of all of my forces in the y direction, which was 5.2, my mass of 0.3 kilograms, and now solve for the y component of my acceleration. If you go ahead and do this, you'd find that your acceleration in the y direction turns out to be about 17 meters per second squared. Again, I'm going to make a little bit more room as we finish this problem up. What you're going to find now is that if we were asked for the total acceleration of this hockey puck, acceleration, remember, is a vector quantity and requires both a magnitude and a direction. All I really have at this point is the total magnitude of the acceleration of my puck. In fact, if I were to draw a separate diagram of just the acceleration of my hockey puck, I could draw another diagram here, and I'd find that if this was my hockey puck, I would have an acceleration of 29 in the x direction and an acceleration of 17 in the y direction. The total of this, if I were to now solve for my total acceleration, would be this resultant vector that would be popping up here. So the question is, what is the magnitude of this resultant vector for our acceleration? And where is it pointing? What is the direction? Because vectors are going to include both of those pieces of information to fully answer that. When I solve for this, I could easily solve for the total magnitude of my acceleration by simply using a Pythagorean theorem. If I square both the 17 and the 29 and take the square root of that, I'll get my total acceleration for this hockey puck. Again, if you want to plug that into your calculators, you'd find that that turns out to be about 34 meters per second squared as the total acceleration of the object. But again, since this is a vector, I also want to give a direction for that, and direction for vectors are always given by an angle. So if I want to set up an equation for solving for theta, I could set up a tangent function where the tangent of theta is going to be equal to the opposite, or the 17, over the adjacent, or the 29. Solving for theta by taking the inverse tangent of both sides gives me an angle or a direction of this acceleration of about 30 degrees. So my total acceleration of the hockey puck is about 34 meters per second squared at a 30-degree angle, measured counterclockwise from the positive x-axis. This gives you just a bit of an introduction to force problems and how we can solve for accelerations or other types of questions utilizing Newton's second law. When you come back to class, we'll try some more examples there.